So at this point, you should have started the lesson by watching the video on the periodic table from Crash Course. It talked a little bit about periodicity in the video, and I want to talk more about that now. So what is periodicity? Well, it's patterns of physical and chemical properties that repeat at regular intervals on the periodic table. These patterns are what help Mendeleev organize the periodic table. So what he did, and you saw in the video, that he wrote down properties of elements, and some of them were similar. He put them together, and eventually grouping things together caused the periodic table to form out of his patterns, and that was all based on periodicity. So I want to take a look at group 1 here. These are the alkali metals. There are 6 of them pictured there. Firstly, they're in group 1, so they have one valence electron, and this electron can be easily removed, and that causes them to be highly reactive. They do not occur naturally. If they did occur in nature, they would react with water and they would explode, so they're not in nature. And these are soft, gray, and shiny. Now I'd like to take a quick look at these metals reacting with water. And pay attention to this because we're going to be doing a lab coming up, and we're going to need to sort of refer back to this video we're about to watch.
There are 6 alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our 5th alkali metal. There are 6 alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkali metal.
I'd like to talk now about the group 2 alkali earth metals. So they're group 2, so they have 2 valence electrons. They are less reactive compared to group 1. And the reason they're less reactive is because they're harder. So they're more stable, meaning they are harder metals. So they're not soft. You can't cut these with a knife. And because they're nice and hard, it's probably no surprise that they have high BP boiling points and high MP melting points than the softer group 1 metals. I want to jump ahead to group 7. And we skip groups 3, 4, and 5, and 6 because they have metals, nonmetals, and metalloids. So it's hard to get periodicity when you've got sort of a natural change in things. And when we get to group 7, we have all nonmetals. So it's easy for us to take a look at the patterns here. So with the halogens, they are highly reactive. They're in the gaseous state. They're diatomic. So Cl2, F2I2, and Br2. They're made of 2 atoms each. And they are less reactive going down the group. So fluorine's at the top. It's the most reactive. So if you think about it, metals get more reactive going down the groups, and the nonmetals are the exact opposite. They get less reactive going down the group. I'd like to take a look at another little video here that shows how these things are quite reactive.
Here are the 4 halogen elements: fluorine, chlorine, bromine, and iodine. Fluorine on the left is almost colorless. Next comes chlorine, which is greenish yellow. Fluorine and chlorine are both gases at room temperature, but bromine is a liquid and iodine is a solid. Even so, they're both quite volatile. You can see the colored vapors, orange-red above the liquid bromine and purple above the solid iodine. Whether solid, liquid or gas, the halogen elements consist of diatomic molecules, F2, Cl2, Br2 and I2. Fluorine reacts often ferociously with almost everything else. A stream of fluorine instantly sets iron wool on fire, and it does the same thing to charcoal. Now let's see the reaction with hydrogen. There's hydrogen in the balloon. A jet of fluorine gas pierces the balloon and explodes with the hydrogen inside. Let's see it again in slow motion. Now you can see the fireball more clearly. Now the reaction between hydrogen and chlorine. I light the hydrogen at the jet and lower it into a jar of chlorine. The hydrogen carries on burning, but with a pale blue flame. When the halogens react with hydrogen, the hydrogen halides are produced: HF, HCl, HBr, and HI. In each compound, the halogen has a valency of 1. All 4 compounds are gases. They're also very soluble in water. Here's water swallowing a jar of hydrogen chloride. Now let's see how the halogens react with aluminium. When aluminium powder meets fluorine gas, the reaction's over in a flash. To get chlorine to react with aluminium, I'll heat some foil in a stream of the gas. The white fumes are aluminium trichloride. With bromine, I just drop aluminium foil into the liquid. There's a short delay, but normal service is soon resumed. Once the reaction gets going, it quickly takes on the appearance of a pit of hell. As with the chlorine reaction, there's white smoke. That's aluminium tribromide. The reaction with iodine is just as spectacular. A little warming helps to get things moving, but once the reaction's off, it needs no further assistance. The products of all four of these reactions are white solids, and they're all trihalides. Al3, AlCl3, AlBr3, and AlI3. Now, aluminium is a trivalent element, so in these compounds the halogens are all showing a valency of 1. That valency of 1 is also satisfied when the halogen atoms bind to one another in the diatomic molecules with which I started this sequence.
And the last group we're going to look at here is group 8. These are all gases, and they're the noble gases. If you put electricity into these gases, you can get the neon lights, the different colors shown in that picture. So these atoms, they have a full valence shell. We've drawn the Bohr Rutherford. We've seen the full shell. And this makes these gases very stable, and they do not want to react. They've already got a full shell, no reason for them to react. So these gases exist as only a single atom, known as the monatomic gases. So don't confuse those with the diatomic gases. Let's take another look at a short little video.
Here are 5 of the 6 noble gases: helium, neon, argon, krypton, and xenon. They're all colourless and transparent. Krypton and xenon form compounds only with difficulty. Helium, neon, and argon don't form compounds at all. As we descend the group in the periodic table, the atomic number and the relative atomic mass increases. The gases get denser. Helium is lighter than air. Neon is just lighter. Argon and krypton, I've just got to unstick these from the anchorage for a moment. Argon and krypton are both heavier than air. And xenon is the heaviest of the lot. You've heard of a lead balloon? Well, this is it.
So a final summary here on what we've discovered. So periodicity continues across periods, but is interrupted by the transition from metals to metalloids to nonmetals. And that's the exact reason we didn't talk about groups 3, 4, 5, and 6. I mean, there are elements in there that are similar to each other, but generally we wanted to look at kind of the larger set of atoms that were similar to each other. So generally, the larger the metal, the higher the reactivity, and that's related to the ionization energy. Think francium. And generally, the smaller the nonmetal, the higher the reactivity, except for group 8, we eliminate that one. And that's related to the electron affinity. So those two are opposite of each other. So at this point, I'd like you to move on to the homework, and let's get that done.